Happy New Year and welcome to the very first wolfSSL live webinar of 2024. Getting started with wolfSSL in 2024, present by wolfSSL Engineering Manager Chris. My name is Shizuka and I'll be moderating this webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I'll invite you to follow us on Twitter at wolfSSL, as well as our other socials. Also, feel free to email us if you have any additional questions. And now I'd like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is of course supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-178 support, HIPS certification, and a HIPS ready offering, MQTT up to the V5 specification, SSHB2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support and commercial support for Coral. All of these offerings are accompanied by through maintenance and support plan up to the 24/7 level. We also offer full service consulting. And now I would like to turn it over to Chris to talk about getting started with wolfSSL in 2024.
Thanks, Shizuka. Hey everyone, like Shizuka mentioned, my name is Chris Conlon, Engineering Manager here at wolfSSL. Thanks for joining us for our first webinar of the year. This is going to be our agenda today. We're going to start with an overview of SSL and TLS 1.3. Then we'll move into talking about wolfSSL as a library, look at an overview of the library, what the package looks like when you download it, how you can build it, run a couple of our example applications for testing and benchmarking our cryptography library, look at some basic library usage, a few debugging tips, and then if everything works as expected, I'll give you a quick demo of our test and benchmark application, hopefully ending with some time for Q&A at the end. So starting out, let's go over kind of a quick introduction to SSL and TLS. There's been several revisions to this protocol over the years, starting in 1995 with SSL 2.0 being the first version that was released. SSL proper in 2.0 and 3.0 are now both considered insecure. In 1999, the protocol changed enough that it warranted a name change to transport layer security. There's been 4 revisions of that, 1.0, 1.1, 1.2, and 1.3, most recently in 2018. And then DTLS has been paralleling the development of TLS, DTLS standing for datagram TLS. That would be a variant of the protocol you would use over an unreliable transport medium, such as UDP. TLS 1.3 is the most recent version of the protocol. This shows you the development timeline as far as drafts between when work started in August of 2013 and when the final RFC was awarded in August of 2018. TLS 1.3 is RFC 8446 for reference. If you're curious, you can always go look that up on the internet and read through all the nice technical details there. There were a few things that changed in TLS 1.3. These are kind of some of the highlights. So there were algorithm changes. The protocol designers took out a lot of the older insecure features. Most of the handshake messages are different, and a lot of them now are encrypted. So a person eavesdropping on the connection can't see a lot of the details that happened before in previous versions of the protocol. There's a new 0 RTT or 0 round trip time mode where application data can be sent up front early with the client hello. There's some redesigned key derivation functions and also changes to how session resumption are done. So what are the big advantages to you as a user? The first one being faster performance. So TLS 1.3 requires 1 complete round trip to establish the handshake. Previous versions of the protocol, for example, TLS 1.2 required 2 complete round trips. So this is particularly helpful if you're on a high latent network where the 1 less round trip means that your network latency has less of an impact on the time required to establish a connection. Optionally, that new zero RTT mode, if you are in an application environment that can benefit from having data upfront earlier, that can be helpful, although it does require some kind of protocol specification telling you how to safely use that. The second big advantage is it's more secure. So like I mentioned, a lot of the older legacy insecure algorithms or pieces are removed. So you can see some of those that were removed here on this slide. And then also being more secure is that more of those handshake messages are encrypted. It can also be more flexible depending on your use case. There's a new key update message that allows rekeying the session without reestablishing an entire new handshake. And so that can be done anytime after the first initial handshake is done. It does allow post-handshake authentication. So with previous versions of the protocol, you always did the authentication during the handshake. Now you can optionally do that later if you would rather. And then some of those old and legacy features that were removed can help reduce your library footprint size. So that can be helpful if you're on an embedded target or resource-constrained environment. We have a lot of great information on our website about TLS 1.3. This is the best starting point. If you go to wolfSSL.com/TLS13, you can browse and peruse links from there going out. If we take a step backwards, where is SSL and TLS located in the network stack? This is kind of a simplified diagram of the OSI model that shows you that it's layered in between the transport and application layers. The three main goals of SSL and TLS are authentication, confidentiality, and integrity. And then in this diagram, it's just showing you the blue subprotocols here, the SSL, TLS subprotocols. And then the green boxes are examples of application protocols that could either sit on top of SSL and TLS, like HTTPS, or on top of just your transport layer, like HTTP. When the client and server first make the connection, they go through a handshake process. This is a diagram of the TLS 1.2 and earlier handshake, where there's a couple round trips here that establish the shared keying material, maybe exchange certificates and authenticate the peer. And then you end up down at the bottom where you have a secure encrypted channel to communicate over. TLS uses what's called cipher suites. So this is the format that's used in pre-TLS 1.3. And so this is essentially a string representation of the algorithms and modes that will be used in that connection. So you have a protocol followed by a key exchange algorithm, the bulk encryption algorithm in an optional mode, followed lastly by the message authentication function. If you've ever configured web servers or TLS connections, you're probably familiar with what some of these look like. These are some examples of the TLS 1.2 cipher suite list. In TLS 1.3, they changed the cipher suite format and they removed the key exchange and signature algorithm from it. So here you have a more condensed cipher suite string, just with the protocol, the bulk encryption algorithm, the mode, and then the message authentication function. Taking these things out really reduces the cipher suite list. You can see here the kind of complete TLS 1.3 cipher suite list from the RFC. So now that we've kind of done a quick intro on the protocol, now we're going to move on to the wolfSSL library. So wolfSSL itself, we wrote wolfSSL to be very portable, very lightweight. We also want it to be progressive in features. So it does support up to the latest TLS 1.3 and DTLS 1.3. Footprint size, we try to keep down. This can be very configurable depending on what options and what algorithms you want enabled. So the smallest build we've ever done is around 20 kilobytes for a pre-shared key only build. Standard builds, can come in around 100K or so. Runtime memory is 1 to 36 kilobytes of RAM per session. And this footprint size is up to 20 times smaller than OpenSSL. So of course, if you're on an IoT or embedded device, it's going to fit much more easily. We do try to port wolfSSL to pretty much every RTOS and OS we encounter. There's a list of most of the RTOSs and OSs we support on the bottom of the slide here. I think we're upwards of 30 plus at this point, but most likely your operating system is there. If it's not, we can pretty easily add it for you. Some additional features you'll find in wolfSSL include an OpenSSL compatibility layer. This is essentially a couple thousand of the most commonly used OpenSSL APIs that we have the same prototype for, and then internally we map those down to wolfSSL logic internally. So what this can allow you to do is to compile an application that has been using OpenSSL against wolfSSL with very minimal changes. At the most minimal level, just changing the link step from linking against OpenSSL to wolfSSL. We do like to port into a lot of open source projects, which includes a lot of different web servers. So we support all the major web servers today. You can build Apache, Nginx, Lydie, and Mongoose with wolfSSL underneath for the TLS. We also like to plug into hardware-based cryptography. So if you've got hardware crypto on your silicon, we can use that instead of our software-based crypto. This can give you performance advantages and also code size reductions. And we have a pretty big growing list of targets there. We support the NSA Suite B algorithms, and then we do have validated and certified versions of our wolfCrypt library available. So we have FIPS 140-2 for DoD and government consumers. We also have 140-3 currently in coordination. We have a DO-178C DAL-A certificate for wolfCrypt for avionics use. And then if you do need the CAVP only algorithm certificates, we can also offer you those. Sometimes those are helpful to be used in a higher level validation like common criteria. Like I mentioned, we do like to port into some open source projects every year. You can see some of the ones we've done on this slide, but we have a bunch more that we've done. So this means you can compile all these different things with wolfSSL or wolfCrypt underneath. It can be pretty handy, especially if you're trying to get FIPS compliance underneath a lot of these different things. And if you want to see kind of our full list of patches that we maintain, we do have an open source project repository, OSP, which I put the link to on the bottom of the slide here. Some of these we've also submitted upstream where you don't need a patch. wolfCrypt sits underneath wolfSSL. This is our own cryptography library. All these algorithms have been written from scratch and support pretty much all of your standard algorithms in addition to some more progressive ones like Cha-Cha 20, Poly 1305, and Curve and Ed 25519. And most of these can be compiled in or compiled out depending on your needs and footprint requirements. We are starting to integrate post-quantum cryptography support into wolfSSL and wolfCrypt. So we've done this on kind of a stepwise approach. If you've been following the post-quantum algorithm status, you know that NIST is kind of running or has run a post-quantum algorithm competition. They're getting towards the final algorithms in that. And so the first stage we did was, add support for some third-party libraries that already had a lot of the competition entries and finalists implemented. So libOQS, PQM4, the HashSIGs library, and the XMSS reference library. So that allowed you to use wolfSSL and then plug in those underneath to get a post-quantum TLS connection. Now, the next step that we're currently working on is doing our own implementations of kind of the finalist post-quantum algorithm contenders. So I think we're working on Kyber right now and a couple other ones. So we'll roll those out hopefully sometime this year, and you can start to use and see what those are looking like. This gives you a timeline for kind of what we've done as far as post-quantum support in wolfSSL. We started, back in 2021, at least with the most recent rounds. We did support ntrue for a long time back. But you can see we added libOQS support, added some more algorithm support, added support for open source projects like Apache and curl. With the 5.3.0 release, we added embedded post-quantum support on the STM32. You can see we continued to add more algorithm support in 5.5.0, 5.5.1, did some cleanup in 5.5.4, and then most recently, 5.6.4, we added DTLS 1.3, clientello post-quantum fragmentation support. We also added LMS, HSS support, and XMSS support to wolfCrypt. To get wolfSSL, you can either download us from our website. That's where we put our stable releases, or you can follow us on GitHub. We do tag our stable releases there as well. Or if you're someone who likes to track our development release, you can watch what we're doing there on a day-to-day basis. Now, when you download wolfSSL, we do have a lot of things in the package. So sometimes it's helpful just to walk through the package real quick and call out the important things that you might be interested in. So that's what we'll do here on the next couple slides. So the first thing going down from the top that you'll run into is the IDE directory. This is where we keep a lot of our compiler IDE project files. So if you want to open up wolfSSL as a project in Xcode or IAR or Kyle or Rally Crossworks, this is where you would go to just open the project file and hit build and end up with a library artifact. If you keep going down, I'm skipping over some of it, but just kind of hitting the highlights. There's a certs directory. This has example certificates and keys. So this can be helpful for testing, prototyping. We use these just in our own internal tests and also in our examples to just kind of get up and running quickly before you move on to your own. There's a configure script. So this is used on Unix and Linux with AutoComp to configure the library. There's an examples directory. This includes an example client, an example server, an example echo client, and echo server. So these are good examples to look at to see both API usage as well as kind of provide a known endpoint. So if you're developing a client, you can test against our example server or vice versa. We also have a wolfSSL-examples repository on GitHub. So this has some more simple examples. So if you're looking for something like, how do I do RSA signing and verifying? Or how do I do AES file encryption? Those are some examples of things you might find in there. The gencertbuff.pl, this is a Perl script that we use just to generate C arrays from certificate and key files. So a lot of the embedded devices won't have a file system. You can just feed the file into the script and it'll dump out the associated C array version of it into the wolfSSL/certs_test.h header. We'll go down and skip quite a bit of things there and land on the wolfCrypt directory. This is our source file directory for cryptography files. The wolfSSL subdirectory is our header file directory. So just under that wolfSSL is our TLS level headers. Under wolfSSL wolfCrypt is our crypto level headers. And under wolfSSL/OpenSSL is our OpenSSL compatibility layer. Down towards the bottom, you'll find some Visual Studio solution files. There's also some various versions of these in the IDE directory. I believe there's a Win and Win10 directory inside of IDE. You'll find a wrapper directory, second from the bottom. This holds our C# wrapper. No, we do have some other language wrappers for things like Java, Python, JavaScript. Those are ones that are they're big enough that we chose not to put them inside of the wolfSSL package themselves. So most of those will live in a separate repository. So once you've downloaded wolfSSL, how do you build it? So if you're on Unix and Linux, which is kind of probably our most common platform for developers, you can easily use the configure, make, install step. And so configure, you'll give a set of options and that'll configure the build. So it's just as simple as doing a -- enable whatever option you're looking for. You can also do a -- disable. You also just can do configure without any options, and that uses our kind of default, what we think of as kind of our default recommended build for most Unix, Linux type platforms. Here's an example of enabling ECC and enabling DTLS. After configure finishes, then you would run make to compile the library. You can pass preprocessor defines through configure using the cflags variable. So here, if we wanted to define example_define, you could use cflags here. You can also run make check. So this will it'll compile the library and then also run our built-in unit tests and test suite. You'll get a little report at the bottom of make check that tells you what passed and what failed. Hopefully everything is passing. If not, let us know. Once you're done, you can install the library by running sudo make install or make install if you don't require sudo privileges. By default, this is going to be installed into user local. So the headers will get installed to user local include wolfSSL. and the library artifacts into user local lib. The library itself is named libwolfSSL. If you're building a shared library.so or .dylib on a Mac, or if you're building a static library, it'll be libwolfSSL.a. There is a sudo make uninstall target too, if you'd like to uninstall it from those system locations. For those of you on Windows, we have Visual Studio solution files. So I mentioned those when we were doing our walkthrough of the file structure towards the bottom. So we've got the 3 solution files you see at the top here. One of them's, the first one is specific to building wolfSSL with ntrue support. Ntrue is one of the post-quantum algorithms. The second one is a 32-bit library and project solution. And then the third one is a 64-bit library and solution. These solutions do include projects for the library proper, as well as the examples and test suite. And if you want more detailed kind of step-by-step instructions for this, we've got a dedicated page on our website. We do have some users on Windows who like to compile with Cygwin, so that's definitely doable. The required Cygwin packages are GCC automake, autoconf, libtoolmake, and unzip. And then you'd simply just follow the autoconf instructions that we covered for Unix and Linux. In the root of the wolfSSL package, you'll find an install file. This is kind of a good starting point for pointing you in the right direction to build for a certain platform. So for example, if you wanted to build on a microchip platform, you might want to check the install file first, and it'll point you towards the kind of next best place to read how to do that. Some of our users don't want to use our build system, but they just want to pull our source files into their own project directly. So you can do that. You need to look where, what source files and what header files you need to pull in. You'll want the SSL and TLS source files under the /source directory, the SSL and TLS header files under /wolfSSL, the crypto source files under wolfCrypt source, and the crypto header files under wolfSSL/wolfCrypt. Portability has been a primary design goal for us ever since the beginning. So we've tried to abstract out pretty much any of the platform level dependencies. So things like IO or logging, entropy, your C standard library, file system use, threading, all that stuff can be either compiled out or overridden in our abstraction layer. We also have a number of what we call port layers. So if we've already ported to something like LWIP, we have a define that you can just set and it'll enable that port layer. So for example, with LWIP, you would define wolfSSL_LWIP. If you're building on free RTOS, we just have a define called free RTOS. And you'll find a list of these in the wolfSSL/wolfCrypt/settings.h header file. A while back, we introduced a nice feature that allows you to maintain a custom set of your own preprocessor defines for wolfSSL, encapsulated in what we call a user settings header. So if you build wolfSSL with wolfSSL_user_settings defined, then we'll automatically include a header file called user_settings.h. Now, this is meant to be a location where you can define all the defines that you want to customize wolfSSL with, whether that be port layers or algorithm customizations or math library tuning. And then you just have to maintain that one header file from release to release of wolfSSL, which makes it pretty easy and pretty seamless on your end, we found. If you want some example user settings to look at to get started, we do have a good one in the IDE Rally Crossworks ARM directory. We also have some examples configs under the examples/configs directory. We have one that's a user settings that essentially turns on all features. We have one that's a kind of a minimum ECC build. And then we have one that we use with our wolfboot key tools. So the wolfCrypt test and benchmark application, these are 2 applications that ship with wolfSSL. You get them just when you download the package. The wolfCrypt test application is essentially what the name kind of sounds like. It's an application that tests our own cryptography on your platform. So we kind of think this is the best first starting place when you're getting wolfSSL and wolfCrypt running on your platform. We want to make sure all the algorithms are running correctly, because if something at the algorithm level is not working right, when you move to the SSL and TLS level, you'll still run into errors, but it might be harder to track those down at that point. So this essentially runs a bunch of test vectors through all the enabled algorithms in the library. and we'll say either passed or failed. This is compiled by default when you just run make. The executable is called test wolfCrypt, and it lives under the wolfCrypt/test directory. We also ship a benchmark application. This benchmarks all of our cryptography algorithms. This can be pretty handy for comparison of, like software versus hardware cryptography, or if you're trying to do some algorithm tuning or math library tuning. Since we do have a number of options that you can play around with there, running this can give you a good baseline for where you're at as far as performance goes. We do post our own reference benchmark numbers. So if we run this on an embedded target, we like to throw the numbers up on this benchmarks page just for reference. So this is also compiled by default when you run make. Executable is called benchmark, and it lives under the wolfCrypt/benchmark directory, and output will look similar to on the bottom of the slide here. But we'll also look at this again when I attempt to do the live run of this for you in a second. So the default structure of the test and benchmark applications do kind of assume you're on a Linux or Unix type system, meaning they have a main function, they use certificate and key files, and they do run all the either tests or benchmarks on all the algorithms enabled in the library. We can customize that though, since a lot of our users are on embedded targets and some of those might not work well out of the box. So first of all, you can reduce resource usage by defining bench embedded. That'll just use a smaller collection of internal buffers. You can use certificate and key buffers or arrays instead of files by defining one of these three defines here. So use for buffers, 1024, 2048, turn on RSA, keys inserts of the respective size, they're 1024, 2048 bit. Use for buffers 256 will turn on ECC, 256-bit keys. And this will be helpful if you want to put these on something that doesn't have a file system, or you just don't want to worry about copying over the files and keys and getting that set up right. A lot of times on an embedded target, you'll have your own driver code. So you can compile out our main functions in these applications by defining no main driver. Then there will be kind of an entry point function exposed for you to call from your driver code, either wolfCrypt test or benchmark test. You can also run individual algorithms on an as needed basis. So if you just want to run the AES test, there's a function for that. If you just want to run the AES benchmark, there's a benchmark function kind of per mode there, as you can see. I listed one for AES CBC. All right, so basic usage. Generally, this is going to be pretty easy and not too many steps, but let's walk through it so you can at least know where you can start. Then there's lots of ways you can branch off from this going forward. The first thing to do is you want to make sure your application is compiled with the same preprocessor defines as the wolfSSL library was compiled with. If not, you can get some really weird errors, if it's around the math library or some of those areas that we could potentially configure differently. If you're using autoconf and configure, we generate an options.h header. And so when you run configure, this header is generated, and all the defines that were used to compile the library are just put into this header file. So it makes it really easy in your application. The first header file, just include wolfSSL/options.h, and you're good to go. The main wolfSSL header file for SSL and TLS usage is ssl.h. So here you can see we're including wolfSSL/ssl.h. We have two main structures. We have a wolfSSL structure and a wolfSSL CTX structure. The wolfSSL structure represents a session. So this would be essentially representing a connection. So you might have multiple of these in your application. The wolfSSL CTX structure is a context. This is a factory for sessions. So typically your application would have one wolfSSL CTX, and then you would make multiple sessions from that. You want to initialize the wolfSSL library by calling wolfSSL init. If you want debugging logs to come out, if you've compiled the library with debug support, you can call wolfSSL debugging on. And then to turn off debug logging at runtime, you can call wolfSSL debugging off. Next, you want to create your wolfSSL context. That accepts a method, a function that represents a protocol and aside. So here we're making a wolfSSL context that's a TLS 1.2 client. You can control how we do peer verification using the wolfSSL CTX set verify. So by default, we will verify the peer, but by default, servers don't verify the client. You can change how that behaves by just passing in the right value here as the second argument to wolfSSL CTX set verify. And then optionally, there's a third argument which represents a verify callback. So when verification fails, we'll call that callback. You can do additional inspection if you need to. Then you'll want to load your trusted root CA certificates. You can do that through a buffer or C array by calling CTX load verify buffer. That can be either in PEM or dir format. Here we're loading one that's in dir format by specifying SSL file type ASN1. You can load a file instead if you want by using CTX load verify locations. Then you would go off, your application would create a socket, it would connect the socket, then you would be ready to make the SSL and TLS session for that socket. So you'd call wolfSSL new, that would give you a wolfSSL session that accepts the context that we created earlier. If you're using regular TCP IP sockets, you can pass the file descriptor to wolfSSL by calling wolfSSL set FD. You would do the SSL and TLS handshake process by calling wolfSSL connect on the client side or wolfSSL accept on the server side. When that finishes with SSL success, the handshake process has completed successfully, and you're just ready to read and write data over your secure channel. You can write data using wolfSSL write, read data using wolfSSL read. When you're all done with that session, you can close it out using wolfSSL shutdown. That'll send the close notify alert to the peer and shut down the session. And then you can free up your resources at the session level, the context level, and the library level. So that's the most basic usage. Of course, there's a lot of other functions you can use for customizing lots of different things. For API details and reference, we do have our wolfSSL API manual online. If you go to our website, you'll find this. This is generated nightly based on a documentation repository we have. So it should be, up to date every night. You can also use our example client as an API reference. That's under the examples client directory, client.c. If you want to use wolfCrypt, we do have one header file per algorithm and one structure per algorithm. So here's an example of AES. So we have a wolfSSL/wolfCrypt/AES.h header file, and then you'd use the AES structure. So that's going to be the same kind of pattern for all of our algorithms if you want to use us just from the crypto level. And then we have the wolfCrypt API reference inside of the wolfCrypt manual, and that's also found on our website. A couple notes about thread safety. wolfSSL is thread safe by design, meaning multiple threads can enter the library simultaneously. We do our best to let this happen by avoiding global data and static data and things that might not work right over a multi-threaded environment. There are two exceptions to this case that you do need to be aware of if you're running us in a multi-threaded environment. So the first is that a wolfSSL session can be shared across threads, but you do need to synchronize access to it. So reading and writing, for example, by two different threads to the same wolfSSL session would result in undefined behavior. The second exception is around the wolfSSL context. So since the context is a factory for sessions, you do need to make sure that's completely initialized before you start making sessions with wolfSSL new. Otherwise, your sessions that you're generating from it might be incomplete. So what we recommend is just having one single thread initialize the context up front. Then you can go off and start your multi-threaded activities. Let's see, debugging wolfSSL. There's a couple things, we have a great support team, and you can always reach out to us at support@wolfSSL.com to get our insight or help on issues. There's a couple things that help, either to help you debug it or help our support team help you. The first one is debug logging. So you can enable debug logging by using the -- enable debug configure option, or by defining debug_wolfSSL. Then anytime after wolfSSL init, you can call wolfSSL debugging on, and you'll start to see debug logs coming out. By default, these will go use fprintf and log to standard error, but we do have a login callback that you can write and register if you want to push those over some other medium. This is kind of what those debug logs would look like. So it shows, when we're entering and leaving functions, it shows details of the handshake process and some more context around that. It shows some details about certificate parsing, and it's going to hopefully allow us to see some context around an error that happens if you run into something. I mentioned you can use our example client server as kind of a known endpoint to test against. So like I said, if you're developing your own client, you might want to consider, try testing against our example server. Or if you're developing your own server, see if you can connect our example client to it. Wireshark is also a very helpful thing. This is just a little snapshot of a Wireshark connection capturing a TLS 1.2 handshake. It does allow you to inspect some of the TLS handshake details. I guess with TLS 1.3, more of those are going to be encrypted, so you won't be able to see as much. But a lot of times, sending a PCAP or a Wireshark trace over to our support team will help diagnose a problem as well. Okay, so now the time has come. Let me see if I can give you a quick live demonstration of compiling the library and running our test and benchmark applications. Just going to switch my screen share over to a terminal window. Make this text a little bigger for you. So this is a wolfSSL 5.6.6, which was our most recent release just at the end of 2023. I downloaded the zip file and unzipped it. And essentially we have here the package structure that we walked through in our slides. So from here we can run configure. That'll go out, detect a bunch of stuff about our platform. I'm not running it with any options here, so I'm just using our kind of default options for, in this case, I'm building on a Mac. That'll set us up to run make here in a second. At the end of configure, you do get a nice summary of all the features that are enabled. If I go to the top, you see you get some information about your system and your compiler and the C flags that we're on, and then a big list of features and if it's on, yes, or no, if it's not. We'll run make to compile the library. So that compiles the library. That also compiles our examples, our test suite, and our unit tests. The actual library name is, if we haven't installed it yet, it's under source/.libs. Here you see I'm on a Mac, so it's wolfSSL.dylib. So now that we've compiled the library, we can run the wolfCrypt test by running wolfCrypt/test/test wolfCrypt. That runs all the enabled algorithms and prints out test passed or test failed. We can run the wolfCrypt benchmark by running wolfCrypt/benchmark/benchmark. This is going to go out and benchmark every enabled algorithm for at least 1 second. And so it's going to give you how much time it took, the throughput of the algorithm in megabytes per second. If you're on a supported platform, you'll see cycles per byte. And then it'll just go through all of our enabled algorithms. So here we had AES. We're going through some of the message digest algorithms now, the HMAX. When we get to the public key algorithms, you'll notice that it changes metrics. It'll change from throughput to in megabytes per second to operations per second. There you can see with RSA and ECC, we switched to operations per second. You do have some options with the wolfCrypt benchmark. Let's see if that helps. So it does accept some options if you just want to run, a certain algorithm or a certain key size. If you want to convert it to a CSV output for easier export. I believe our wolfCrypt test also has some, oh, I guess it does not have options. So if you wanted to clean the library, we do make clean. If you did want to install it, you could do a sudo make install. And then, like I said, if you wanted to uninstall it, you could do a sudo make uninstall. So that gives you kind of a quick rundown there on the wolfCrypt test and benchmark applications. Generally pretty easy to use. So that brings me kind of to the end of my slides at least, but I'm happy to answer or try to answer any questions you guys might have. So I'll go ahead and open it up at this point.
Yes, so there is a question. Is there additional CPU power requirements when using TLS 1.3 over older versions, which is important for low-end embedded hardware?
I guess no additional CPU power requirements are coming to mind. It's still going to be using a lot of the same algorithms. Does session resumption a little different, but I'm not, that still would have been done in a little bit different way with previous versions. So I don't think there would be any kind of obvious CPU power detriments to TLS 1.3.
There's another question. Are there any export limitation for software-based crypto?
Yeah, for us, since we're a US-based company, we do have to comply with export regulations. We have kind of an exception since we're open source that we have a kind of some wording on our download page that says if you're someone in a certain list of countries, then you can't download this product. And how we adhere to that at the moment.
There's another question. Where to use make and where to use sudo make install?
So make we'll just compile the library locally inside of the wolfSSL package. Make install or sudo make install will install it into your system. So if you had another application you wanted to compile and link against wolfSSL, you could do sudo make install first, and then it would already be in your system, and your other application could find it easily.
There's another question. What actually is tested with make check? Is it complete unit? No, complete until test suite covering all crypto algorithm?
Yeah, so make check runs our unit tests, we have Cypher suite tests, and then we also have like a test suite that runs. We have some additional tests that test some features like OCSP, or if you have a certain flag enabled, OpenSSL interoperability. For unit test coverage, we do cover all algorithms. I'd have to check on our exact code coverage percentage, but I know we do test all algorithms for sure.
Another question, can wolfCrypt be used without wolfSSL? What can be use case for such separation?
Yeah, so if you want to use wolfCrypt only, you can do that. We actually have an enable option. I think it's enable crypt only, and that compiles out all the TLS SLTLS code bits. Use cases can really depend on what someone needs to do. If you just needed to do like a signature verify, that would be a common use case. But essentially, it just exposes all the crypto algorithms to you individually, and then you can even turn off the ones you don't need.
Another question, what can be minimal sufficient setup algorithm for low and embedded platforms?
I guess that's going to partially depend on your requirements. If you don't have any requirements, you'll need at least the algorithms to make up one or more cipher suite. So, we see a lot of people who would just, pare it down to like a ECC P256 with, one of the SHAs. We do have a minimum, I believe we have a minimum build configure option. gosh, I can't remember what that's called off the top of my head, but one of our configure options will give you kind of a small minimum build. Or you could use that example user settings.h. We have that minimum ECC one, which would get you pretty close to what I was mentioning with kind of the ECC only build.
There's another question. If we use multiple CA levels, does wolfSSL automatically walk up the cert chain up to the root, or do we have to do that in our app?
If you're using us in the context of TLS, we'll walk up the peer chain that we receive from the I guess the client or server, and you do need to have the right kind of intermediate or root CAs loaded as trusted roots in order so we can have the complete chain. But then we will walk up the chain from leaf to root in order to correctly and completely verify that chain.
Another question, can Wireshark be used both for Windows and Linux?
Yeah, I'm pretty sure they have versions for both of those. Yeah.
Another question, can we get a recording of, yes, you can get the recording of this webinar shortly after this webinar. And another question, what are the spec of the machine which was used for the demo? Is this ARM or x86?
My machine here is a Intel i7, so x86-64, but we also run on the ARM Max if you're curious about that.
And will these slides be made available? Yes, this slide will be available after the webinar. And another question, timeline for HIPS 143 compliance?
Yeah, that is a great question. We're in coordination right now, so which is kind of the last stage that we need to go through to get the certificate. Right now it's we're kind of waiting, so we hoped it to be soon, but we don't have an exact timeline that I can give you for that. And we do actually have two 140-3 certificates in process right now, so hopefully one of those will come out soon.
There's another question. What is the minimum RAM required to put it in microcontroller?
So as far as footprint size goes for flash or ROM, a typical build will be like 60 to 100 kilobytes for like a TLS 1.2 or 1.3 client and server. You can pare that down, if you can eliminate algorithms. So like I mentioned, our smallest build was 21 kilobytes, which is a pre-shared key only build. Now that does kind of restrict you in that you probably need to control both sides of the connection if you're going to be using pre-shared keys. As far as RAM goes, the peak is roughly 36 kilobytes, and that's mainly due to the IO buffers. The TLS specification specifies the maximum TLS record size to be 16 kilobytes. So that's two of those brings us up to the 36K level. That can depend on what math library you're using and how that's configured. I do believe we've got some blog posts that will outline some snapshots of doing like some different configure options and what is the stack and heap usage on those. So those might be some interesting ones for you to do a quick search on, or if you can't find them, let our support team know and maybe we can point you towards that as well.
I do have another question. Does wolfSSL have support for offloading crypto to SSL's accelerator?
We do. So I guess in the terms of an SSL accelerator, we do a lot of hardware-based cryptography, and that's going to be accelerating algorithms. For, I guess, a higher-end accelerator, we can work with more of an asynchronous accelerator like Cavium Nitrox or Intel Quick Assist. For those two, we have a kind of a separate module add-on that we call our async product. But for just microcontroller level hardware crypto, a lot of most of that's just built into the library. So you don't need anything special. You can just get that when you download the library proper.
There's another question on the wolfSSL RTOS multi-threading for the thread safety of objects. You mentioned this was a limitation, but it can be mitigated by using synchronization read/write. Will you elaborate on this and advise where to find information in the API manuals?
Yeah, so for elaboration, essentially accessing the wolfSSL session from multiple threads just needs to be protected with some kind of lock or mutex lock or other synchronization method. And in the API, it is in our manual. We probably have a section on thread safety. I don't recall off the top of my mind what part of the manual that is, but if you get to the manual, you should be able to search for either synchronization or thread safety, and that should take you to that area.
There's another question. What is an expected compile size for AES only on an embedded system, SAMD21?
For AES only, for AES, the biggest part of AES is the AES tables, which are about 10K in size. So I just off the top of my head for AES only, I would guess, a little bit more than that, like maybe 10 to 15K. Unless you have, well, if you have hardware crypto available, that would reduce it a lot. But in that case, you might just be able to use the hardware crypto directly.
There's another question. Can wolfSSL be used in development like in quick protocol development that requires inbuilt TLS?
We can. Yeah, last year, I believe it was last year, we added support for compatibility with NG TCP2 for quick support. So we added the right kind of functions and support that was required from the TLS library at that point.
Another question, could wolfSSL be used for other communication peripherals such as SPI or UART? In case of yes, do you provide any examples?
Yeah, so one kind of nice thing about wolfSSL is that although we default to using a TCP/IP Berkeley BSD API for transport, you can write and register your own input-output callbacks. And so in that framework, if you have those callbacks set up, whenever wolfSSL will encrypt data and then just give your output callback data to send over the transport. And then vice versa, we'll call the input callback whenever we need data. The transport layer can give it to us, and then we'll handle decrypting and processing it. So you can do TLS over any kind of transport layer, essentially. We have people doing it over serial buffers or serial lines. We have people doing it over memory buffers where you don't even have a transport available at all. And I think you could use that same framework to communicate over SPI or UART over TLS, if that's what you were meaning. We do have some examples in that wolfSSL examples repository, I believe, of doing some custom IO.
I do have another question. Do you plan to support STM32H573 H5 family?
Yeah, I want to say we already have support for STM32H5, but if you check on the website and we don't have that listed anywhere, reach out to our support team and we can give you some more guidance around that. Generally, we're pretty portable across platforms as far as, an STM32 would be considered.
There another question. It is normal for the TLS negotiation between the server and the client to last 2 seconds using PIC32. That's why I have to keep an MQTT socket connected.
I guess that's maybe a harder one to answer without running the wolfCrypt benchmark first and seeing what you're getting as far as crypto performance goes. Because that's going to probably be the bottleneck kind of with your handshake process is going to be the asynchronous operations like RSA or ECC. So if you ran the wolfCrypt benchmark and saw, okay, here's how many operations per second I'm getting, does that line up with a 2-second handshake time, factoring in your transport latency, anything like that? some of our more extremely embedded platforms, that's probably not out of the question. But again, we can also try to give you some more insight through our support team. If you want us to help you get the benchmarks running or kind of do some analysis there if you've already run them.
There's another question. Does HIPS mode add as much overhead to embedded systems?
So with FIPS, we don't, I guess, first of all, we don't really have a FIPS mode. We just have a FIPS library and a non-FIPS library. So we don't allow you to switch like from into and out of FIPS mode, either compiling and using the FIPS library or not. But then after that, in the FIPS library, there's a couple specific things that are added. There's a power on integrity check that runs an HMAC SHA-256 over the object files in memory. There's also a set of known answer tests that run over all the algorithms inside the FIPS boundary. So you do incur some overhead, but that only happens, kind of once, either at startup when that library is first initialized, or with 1.3, it can happen on demand. So like when AES is used for the first time, the known answer tests for that algorithm run. So you're going to incur a little bit for some test vectors to run, but only one time, and it should be not too impactful in the grand scheme of things.
And I do have a last question. Do you support integration with ThreadX and a NetX duo?
We do, yeah. We supported ThreadX for quite some time now. I think we have a defined, it's called ThreadX. If you look in our settings, wolfSSL wolfCrypt settings.h, and I think we've done NetX. I want to say that also means NetX Duo, but take a look, and if not, then we might be able to help you out there too.
Perfect. If you guys have additional questions, please email us at fax@wolfSSL.com. And thank you, Chris, for hosting an informative webinar, and everyone for joining this webinar. And please don't forget to follow us on Twitter at wolfSSL, as well as at the socials. Thank you again, and have a nice rest of your day.